Now try to see these two rishis. Okay, you know the rishis which we had millions and millions of years back in our country. We are talking about Maharishi Kannad, okay, and Pakura Kattayama. So now in the context of atoms we are studying, of course, what these two rishis told us. Okay, these saints or rishis told us something that first of all, coming to Kannad, Kannad said that Parmanu is the last particle. Okay, and after that the division of particles is not possible. That was said by Kannad. And Pakuda Kattayama said that they actually, the atoms or the particles move around as combined particles. So if you see, both of them, they told different things. Okay, he was in a polar opposite to what he was. Okay, one said that the last particle is there, Parmanu, and the other said that they combined move around. So obviously they contradicted each other, but more importantly, it's not about just India. Okay, philosophers outside also said certain theories. Let's try to see. So Democritus and Leucippus, they also gave us theories. They told us that indivisible particles are atoms. The final particle we were talking about, they are indivisible particles and they are called atoms. Okay, so they were Indian, the first two rishis we talked about. These philosophers were Greek. Okay, these Greek philosophers, Democritus and Leucippus, said or rather constructed the theory of atoms, that is the indivisible particles. But all these theories were not proved in any form. The final proof came from two other philosophers or two other scientists rather, who proved the theory, and now we are going to study them. Before that, who are they two? We are talking about Lavoisier and Proust. These two people, these two scientists actually proved a certain thing. They proved two chemical solutions. Okay, two solutions, two theories which we are going to remember completely. So we'll not just randomly note down the theories, we'll also try to prove it. Okay, so first experiment we will be having, through which we are going to prove the first theory. Okay, let's do it. Okay, so to prove the first theory right, we need certain things. First of all, we need a cork, you know, a cork. Okay, then we need a conical flask, you can see this. Then we have an ignition tube, test tube, which we use normally. Then the two solutions, very important. First of all, we have a copper sulfate solution, and then we have a sodium carbonate solution. Okay, to perform the experiment, we need these 5 things essentially. Now what do we do with these? Let's try to do it. Okay, so initially you saw the cork. The cork will be put like right at the top of the conical flask we have. Okay, then here you can see the ignition tube, the test tube. Okay, it will be dipped through a thread. You can see the thread, it's actually mentioned also. Okay, here it's written, it's a thread. So it will be hanged through a thread, the ignition tube. And you know, we had two solutions. We initially had the copper sulfate solution and the sodium carbonate solution. So the copper sulfate solution will go inside the tube, the ignition tube, you can see. It will go inside the ignition tube, and the sodium carbonate solution will be outside it. Okay, so now try to see once more. Okay, visualize it in front of you. You may have to perform the experiment also, but even if you don't perform, try to visualize it properly. Okay, now once you do this, try to measure the weight of this entire system, whatever is in front of you. Try to measure the weight. Okay, you will get a certain weight, and after you do that, after you measure the weight, you will try to move and shake that entire conical flask once. Try to shake it, and you know, when you shake it, this solution can actually come out and get mixed with the other solution, that is copper sulfate may get mixed with sodium carbonate. So of course, two chemicals are getting mixed, some difference may occur. So after that difference, after that reaction or whatever is happening, try to again measure the weight. Okay, you will observe certain things, and that are the things we are going to talk about. Okay, so once more I am summarizing what did you do. Initially in this system you will measure the weight, and then once you shake the entire conical flask, you will again measure the weight. Like after a supposed chemical reaction, you will again measure the weight. So some difference may occur. Now what are the differences? Let's try to see it. Firstly, the solution will likely turn a pale blue-green color. Okay, two different chemicals are there. Of course, there can be a chemical reaction. There has to be a chemical reaction rather. So there will be a turning into pale blue-green color. You saw initially, I'm again showing it to you. You saw that copper sulfate was blue and sodium carbonate, you can see no color, like it's colorless. But it will turn into pale blue-green color. That is the first thing. Secondly, a chemical reaction, we have been talking about this, has taken place. This is evident from the color change and the formation of a precipitate. So, obviously, pale blue-green color from an absolute blue chemical and a colorless chemical. Of course, this can't happen without a chemical reaction. So, a chemical reaction has taken place and also a precipitate has formed. So, these two things, the color change and the precipitate formation, shows that a chemical reaction has taken place. Next. Now, once I am actually going back to the picture once to show you something. You saw that a cork has been used at the top, right? Like over this flask, a cork has been used. You may think, why is it being used? Okay, you may actually think, and that's actually a good question because that's for a reason. What's the reason? A cork should be put on the mouth of the flask to prevent the loss of any gaseous products that might be formed during the reaction. In this specific reaction, carbon dioxide is produced. Okay, so a cork is actually put at the mouth of the flask because in any reaction, you know, like we have now proven it that there has been a reaction, right? It has been proven by us. So in that case, you know that whenever there is a reaction taking place, some gas or some output is coming out. Okay, and in that case, that output, particularly when it's a gaseous output, in this case definitely it is carbon dioxide as mentioned. So that can go out, that can travel out of that conical flask we are talking about. So that has to be trapped. To trap that, to ensure that that gas doesn't go out, you need a cork. Okay, now another final observation, which is again the most important observation I must say, that is, ideally the mass of the flask and its contents should remain constant before and after the reaction. This is in accordance with the law of conservation of mass. First of all, remember, I told you to do something. I told you to weigh the entire system before mixing them, right? Before mixing the two chemicals. You got a certain weight. After mixing, like after the reaction took place, you are again supposed to weigh that. And very surprisingly, you will see that in both cases, the weight is similar. It's the same weight. Why is it so? That will let us know the law of conservation of mass. Because of this law, that is the first law given by Lavoisier and Proust, the mass will remain same before and after the reaction. Now, let's try to define this law, okay? The law of conservation of mass states that mass is neither created nor destroyed in chemical reactions. In other words, the mass of any one element at the beginning of a reaction will equal the mass of that element at the end of the reaction. In this case, you saw different chemicals. In any other case, any other two chemicals you can take, it will always be same. The mass will always remain the same. Okay, so it can neither be created nor be destroyed. In this case, you saw, I told you to weigh it before, I told you to weigh it after the chemical reaction took place. But in both cases, it's the same. Because mass can, this is the key word, it can neither be created nor be destroyed in chemical reactions. Okay, that is the main keyword. You have to define it like this. Like the second line, you can like twist it a bit, just try to explain it. But this thing, this statement, mass can neither be created nor be destroyed in chemical reactions. You need to essentially remember this. Okay. Oh, now a question for you. The law of conservation of mass states that mass cannot be created but can be destroyed. So is it true, option A, or is it false, that is option B? The correct answer here is option B, that is false. as we discussed, very critically you need to remember that mass can neither be destroyed nor be created. So in this case we have told cannot be created but can be destroyed, right? Can it be destroyed? No, it can't be destroyed. Mass can neither be created nor be destroyed. Need to remember this completely. Okay, so here the answer is false. Okay, so Lavoisier and Proust also gave us another theory. Let's try to see it. Before that, we'll be studying a very interesting thing, that is the sources of water. So the drinking water you are having, and it's not just for drinking, you can use it for other daily works also. So in that case you can obtain that water from many sources, right? It can be from wells, then rainwater, streams, then you have rivers, tap water also, the basic one we use, and then lake also, and many other sources. I just mentioned 6 here, but it can be more than that. Now you know that water, the formula, what is the formula of water? It's H2O, right? We all know this by now. So it has hydrogen and it has oxygen. In any water source, you may obtain the water from tap or from rain, from well, or any other, the other 3 sources or any other source which you know. You can obtain water from any source. It will still be having this H2 and O. The formula of water, you obtain it from anywhere, it will remain the same, right? Now it's not just about having hydrogen and oxygen, okay? It's also having it in a very definite proportion. We are talking about a definite proportion in which the hydrogen and oxygen is divided. So try to see this. 2H2 plus O2 give us 2H2O. You can see 4 gram and 32 gram is the ratio, and the ratio is 1:8 by mass. So H is to O is equal to 1:8. Now let's get back to the previous page. In any source of water, you will be having hydrogen and oxygen, of course, H2O will be the formula, and you will be having this ratio H is to O as 1:8 only. It won't be changing as per the source. Now if you go to some other source, suddenly the ratio of H and O, hydrogen and oxygen, won't change. It will always remain this constant proportion, the constant ratio, okay? And from this we come to another very important law. Before that, this law of constant proportions that we are talking about states, what does it state? In a chemical substance, the elements are always present in definite proportions by mass. The law of constant proportions, okay? It states that in any source, like I told for water, it can be for any other element, the elements are always present in definite proportions by mass. Okay, 1:8 will remain 1:8 irrespective of the source, and that's for water. We are talking about any other element. It will always remain that ratio. This you need to remember. So law of definite proportions. Okay. Now we are going to look into John Dalton's life a little bit. There are many theories given by John Dalton, the atomic theory of John Dalton, which we will be studying in a different video, but for now try to see. John Dalton was born in a poor weaver's family in 1766 in England. He began his career as a teacher at the age of 12. In 1808, he presented his atomic theory, which was a turning point in the study of matter. So as I said, John Dalton's atomic theory is of very much importance. His life is also given a little bit. You may remember. His life is also given a little bit. You may remember. And obviously his atomic theory is something which you need to remember. Then he took the name atoms as given by the Greeks and said that the smallest particles of matter are atoms. Now what did I show at the beginning of this video? I showed how the Greek philosophers told that the indivisible particles, okay, indivisible particles are known as atoms. Okay, Democritus, Leucippus, I told that. So he took that name, that is atoms. His theory was based on the laws of chemical combination. So we talked about the law of chemical combinations, the two laws, very important, Lavoisier and Proust's laws, and he actually took inspiration from both of them. Like the Greek philosophers told something about the atoms, the chemical combination laws were there. So he took inspiration from both and tried to provide his atomic theory, which we will be of course learning later. Okay. So now trying to summarize this entire video, what did we talk about? We talked about first of all how the Indian saints and rishis like Kattayama and Maharishi Kannad, they gave us different theories. Like Kattayama said that the particles, the last particles, they actually move together. But again, the concept of Parmanu was given by Kannad. Okay, that is like the last particle. Then we talked about the Greek philosophers. Okay, Greek philosophers like Leucippus and Democritus, they said the concept of atoms, like atoms are the indivisible particles. But we also understood that they are just random theories, nothing was proved, which is why we needed some proved law which was given by Lavoisier and Proust. They gave us the two laws of chemical combination. First one was law of conservation of mass, which said that mass can neither be created nor be destroyed. Okay, mass will always remain the same. And then we got the law of definite proportions, which says, like we studied the example of water, in any source of water, the ratio of hydrogen and oxygen will remain the same, that is 1:8. Okay, and there will be constant proportions of hydrogen and oxygen. And this you can study this for any other substance, like it doesn't essentially need to be water. Okay, and then we also took a little note about John Dalton's life. John Dalton, how he actually tried to combine the two theories, like the Greek philosophies which based on atoms and then the chemical combination laws. He tried to actually combine them and give us the Dalton's atomic theories, which we will be actually studying in a later video. Okay, so these are the takeaways from this video.